Welcome! In this session, we'll explore problem number 1259, handshakes that don't cross. This is a fascinating problem that challenges us to think critically about combinatorics and dynamic programming. Let's dive in and see how we can solve it step by step. Imagine you are at a social gathering with N people, where everyone is required to shake hands with exactly one other person. The handshakes are represented as straight lines connecting pairs of people. Now, a handshake is considered to cross another if the lines representing the two handshakes intersect. For instance, if person A shakes hands with person B, and person C shakes hands with person D, but their handshake lines intersect visually, that would be a crossing. The goal of this problem is to determine how many ways the N people can shake hands such that no two handshake lines cross. The input will always be an even number N, representing the total number of people, and the output should be the total number of valid arrangements of handshakes. Since the number can grow very large, the answer should be returned modulo 10⁻9 plus 7, which ensures that the result fits within standard computational limits. Let's review the input and output formats. The input is a single integer n, where 0 equals n equals 1000 and n is always even. The output is an integer representing the count of non-crossing handshake arrangements modulo 10⁻9 plus 7. Let's start with a small example to understand the problem better. When n equals 2, there are only two people in the gathering. Since they both need to shake hands, there's only one way for them to do so without any crossing, by shaking hands directly with each other. Therefore, the output in this case is 1. Now, consider n equals 4. Here, there are 4 people, and we need to find all possible ways to arrange their handshakes such that no two handshakes cross. The answer for this case is 2, and we will explore why shortly. For n equals 4, the two valid handshake arrangements are as follows. First, person 1 shakes hands with person 2, and person 3 shakes hands with person 4. Since these pairs are independent, there's no possibility of crossing. The second arrangement is when person 1 shakes hands with person 4, and person 2 shakes hands with person 3. Again, these pairs are independent, so no handshakes cross. These two arrangements represent all possible non-crossing configurations for n equals 4. Now, taking it a step further, when n equals 6, there are 6 people, and the number of valid handshake arrangements increases to 5. This is because as the number of people grows, the number of ways to arrange non-crossing handshakes grows in a combinatorial fashion. Finally, let's summarize the constraints and edge cases to keep in mind. The total number of people, n, is always an even integer ranging from 0 to 1000. For edge cases, if n equals 0, the output is 1 because there are no people, and thus no handshakes or crossings. When n equals 2, the output is also 1 because there's only one possible handshake arrangement. For larger values of n, the computation must be efficient due to the constraints, and the modulo 10⁻9 plus 7 ensures the results remain manageable. Solving this problem involves understanding how to calculate these non-crossing arrangements systematically, which we'll dive into in the solution approach. To solve the problem of determining valid handshake configurations that don't cross, we first consider the brute force approach. The intuition behind this method is straightforward: generate all possible ways to form handshakes among the given people and then check each configuration to see if any handshakes cross. This would involve drawing the lines for each pairing and analyzing their geometry to verify if intersections occur. However, this approach has a significant drawback. Generating all possible pairings involves combinatorics, which results in exponential time complexity, specifically O(n). On top of that, the process of checking each configuration for crossings adds further computational overhead. Consequently, this method is computationally infeasible for larger values of n due to the factorial growth of the number of pairings. To address this, we turn to a more refined approach using dynamic programming. By leveraging the structure of the problem, we observe that it aligns with the properties of the Catalan number sequence. The key idea is that every valid handshake configuration can be built recursively by dividing the circle into smaller, independent subproblems. For instance, if person 1 shakes hands with person K, this handshake creates two separate groups, the people between 1 and K, and those outside this range. Both groups must independently satisfy the condition of valid handshakes. This insight forms the foundation of our dynamic programming solution. Building on this insight, we define the recursive relation for our dynamic programming approach. Let dp I represent the number of ways to form valid handshakes among two I people. The recurrence relation is as follows: dp I is the sum of dp j multiplied by dp I1 j, where j ranges from 0 to I. This formula captures the idea that for each possible handshake pairing, the left and right partitions of the group can be solved independently, and their solutions are combined. The base case for this recurrence is straightforward: dp 0 equals 1, as there are no handshakes possible among 0 people. In terms of complexity, calculating dp I involves a nested summation over I terms, resulting in a time complexity of O(n) squared. The space complexity is O(n), as we only need to store the dp table to keep track of the results. Given these characteristics, the dynamic programming approach is both efficient and well-suited to the problem's structure. By avoiding redundant calculations and reusing solutions to subproblems, this approach offers significant improvements over brute force. The brute force method, while intuitive, is computationally prohibitive due to its exponential growth. In contrast, dynamic programming leverages the recursive structure of the problem, efficiently producing results even for larger inputs. By adopting the dynamic programming approach, we can solve the problem with a time complexity of O(n) squared and a space complexity of O(n). This method strikes a balance between clarity, computational efficiency, and scalability for larger values of n. It avoids the prohibitive cost of brute force by breaking the problem into smaller, manageable subproblems and reusing solutions wherever possible. As a result, this approach is not only elegant in its use of the Catalan number properties but also practical for real-world applications where performance matters. In summary, dynamic programming provides a robust and efficient solution to the challenge of determining valid handshake configurations without crossings, making it the chosen strategy for this problem. To tackle the problem of determining intersecting handshakes, we start by representing the scenario mathematically. Imagine n people standing in a circle, each shaking hands with one other person. A handshake can be visualized as a straight line segment connecting 2 points, A, B, where A and B are the individuals involved, and we always assume A less than B to avoid ambiguity. The key question is, when do two such line segments intersect? Geometrically, two segments, A, B, and C, D, cross each other if the order of their endpoints alternates, meaning either A less than C less than B less than D, or C less than A less than D less than B, holds true. With this condition defined, a brute force approach can be developed by generating all possible handshake pairs and checking each pair for intersection using the condition. While this method is simple to understand, it involves checking every pair, resulting in a time complexity of O(n) squared. This inefficiency makes it less viable for large values of n and motivates the need for optimization. The brute force method can be implemented using two nested loops to iterate through all pairs of handshakes. For each pair, the intersection condition is evaluated, and a counter is incremented whenever an intersection is found. However, to improve efficiency, we can transition to an optimized approach. By representing all handshakes as an array of tuples like A_1, B_1, B_2, we can sort these tuples by their starting points, A_I, and use a secondary sort on their endpoints, B_I, for ties. This allows us to process the handshakes in a systematic order. A further optimization involves using a sweep-line algorithm or a segment tree. As we process each handshake, A, B, we count how many previously processed handshakes intersect with it. This is achieved by maintaining a dynamic data structure, such as a balanced binary search tree, that tracks active handshakes and supports efficient querying. Edge cases must also be considered, such as when there are no handshakes or when all handshakes are independent. Furthermore, the algorithm must handle scalability for large values of n to ensure practical usability. The intersection condition is key to solving this problem. Two line segments intersect if one starts within the range of the other and ends outside that range. Sorting the handshakes simplifies the problem significantly, as it ensures we can process them in a linear order, reducing the complexity of checking for intersections. The use of efficient data structures, like a segment tree or a balanced binary search tree, allows us to maintain the set of active handshakes dynamically and to query for intersections in logarithmic time. This reduces the overall complexity of the optimized approach to O(n) log n, a significant improvement over the O(n) squared brute force method. From a data structure perspective, an array is used to store the handshakes as tuples, while the segment tree or balanced binary search tree is crucial for managing active handshakes and performing efficient intersection queries. The complexity analysis highlights the stark difference between the two approaches. While the brute force method struggles with quadratic time complexity, the optimized approach leverages sorting and efficient querying to achieve a much faster runtime. The pseudocode implementation starts by sorting the list of handshakes by their starting points, followed by their endpoints for ties. A segment tree or balanced binary search tree, represented here as active_handshakes, is initialized to keep track of the handshakes currently being processed. For each handshake, A, B, in the sorted list, we query that active_handshake structure to count how many of the current active handshakes intersect with A, B. This intersection count is added to the total. After querying, the current handshake is added to the active_handshake structure to ensure it is included in future queries. Once all handshakes have been processed, the total intersection count is returned. This approach ensures that each handshake is processed efficiently, leveraging the power of the segment tree or balanced BST to maintain a logarithmic query and update time, making it both scalable and performant for large input sizes. This Python implementation solves LeetCode problem number 1259, handshakes that don't cross, using a dynamic programming approach. The problem asks us to compute the number of ways people in a circle can shake hands such that no handshakes cross. The key observation is that this problem relates to the Catalan number sequence. Explanation of the code *. 1. The function number of ways takes number_people as an input, representing the total number of people in the circle. If the number of people is odd, it directly returns 0 because an odd number of people cannot form non-crossing pairs. 2. The mod variable is set to 10 to the power of 9 plus 7 to ensure all computations stay within modular arithmetic limits, as required by the problem. 3. An array DP is initialized with size number_people plus 1. The DP I value represents the number of ways to arrange I people in non-crossing handshakes. The base case is DP 0 equals 1, meaning there is exactly one way to arrange 0 people, an empty circle. For, the outer loop iterates through even values of n, as only even numbers of people can pair up. For each n, we calculate dp n by considering all possible partitions of the circle. 5. The inner loop iterates through I, the number of people on one side of a chosen handshake. The formula dp n plus equals dp I asterisk dp n a2 calculates the product of ways to organize the left and right partitions formed by the handshake. 6. To prevent overflow, the result is taken modulo mod at each step. 7. Finally, the function returns dp number_people, which contains the answer for the given input. This approach efficiently computes the result in O, n squared, time complexity, leveraging the recursive structure of the Catalan numbers. The space complexity is O, n, due to the dp array. This is the Java implementation of the LeetCode problem number 1259. Handshakes that don't cross. The logic mirrors the Python implementation, with type declarations and Java-specific syntax for arrays and modular arithmetic. The DP array is used to store the number of ways to form non-crossing handshakes for different group sizes, and the result is calculated iteratively. The use of modulo operation ensures that the result adheres to the constraints of large numbers typically encountered in such combinatorial problems. To solve the problem, we start by considering the smallest case, where the total number of people is 2. In this scenario, our dynamic programming array, dp, is initialized as 1, 0, 0. The base case, dp 0 equals 1, represents the fact that there is exactly one way to pair 0 people. We also define a modulus constant, mod equals 10 to the power of 9 plus 7, to handle large numbers and ensure all calculations stay within bounds. Now, for n equals 2, the outer loop begins. Inside, the inner loop starts with I equals 0. Using the formula dp n plus equals dp I asterisk dp n in a2, we calculate dp 2 plus equals dp 0 asterisk dp 0, which evaluates to 1. After updating the dp array, we get 1, 0, 1. The result for this case is dp 2 equals 1, meaning there is exactly one valid way to perform non-crossing handshakes with 2 people. In the next example, we examine the case where the total number of people is 4. This time, the DP array is initialized as 1, 0, 0, 0, 0 to accommodate up to 4 people. Again, DP 0 equals 1 serves as the base case, and we use the same modulus constant, mod equals 10 to the power of 9 plus 7. For the first iteration, where n equals 2, the inner loop runs with I equals 0. The formula dp n plus equals dp I asterisk dp n a2 gives us dp 2 plus equals dp 0 asterisk dp 0, resulting in dp 2 equals 1. After this step, the DP array updates to 1, 0, 1, 0, 0. This prepares us to handle the next iteration for n equals 4. Now, we proceed with the iteration for n equals 4. The inner loop first sets I equals 0, and applying the formula, we compute dp 4 plus equals dp 0 asterisk dp 2. Since dp 2 equals 1, this results in dp 4 equals 1. Next, the inner loop continues with I equals 2. Here, we calculate dp 4 plus equals dp 2 asterisk dp 0, which adds another 1 to dp 4, making it 2. At the end of this iteration, the DP array becomes 1, 0, 1, 0, 2. The result for this case is DP 4 equals 2, meaning there are 2 distinct ways to organize non-crossing handshakes among 4 people. For the case where number underscore people equals 6, the DP array is initialized as 1, 0, 0, 0, 0, 0, 0. The base case remains dp 0 equals 1, and the modulus constant, mod equals 10 to the power of 9 plus 7, ensures calculations remain manageable. Starting with n equals 2, the inner loop runs with I equals 0. Using the formula dp 2 plus equals dp 0 asterisk dp 0, we find that dp 2 equals 1. After this step, the DP array updates to 1, 0, 1, 0, 0, 0, 0. This concludes the computation for n equals 2 in this example, setting the stage for further iterations. Now, we handle the subsequent iterations for n equals 4 and n equals 6. For n equals 4, the inner loop starts with I equals 0, where dp 4 plus equals dp 0 asterisk dp 2, resulting in dp 4 equals 1. Next, with I equals 2, we compute dp 4 plus equals dp 2 asterisk dp 0, which increases dp 4 to 2. The DP array updates to 1, 0, 1, 0, 2, 0, 0. For n equals 6, the inner loop begins with I equals 0, where dp 6 plus equals dp 0 asterisk dp 4, giving dp 6 equals 2. Then, with I equals 2, we calculate dp 6 plus equals dp 2 asterisk dp 2, resulting in dp 6 equals 3. Finally, with I equals 4, we compute dp 6 plus equals dp 4 asterisk dp 0, bringing dp 6 to 5. The final DP array becomes 1, 0, 1, 0, 2, 0, 5, reflecting all valid configurations for 6 people. The result for number underscore people equals 6 is DP 6 equals 5. This means there are exactly 5 distinct ways to arrange non-crossing handshakes among 6 people. This concludes the dynamic programming solution, where the DP array systematically builds up the results for larger numbers of people by combining smaller subproblems. The key insight lies in breaking down the problem into pairs and using the established formula to ensure every configuration is accounted for efficiently. To analyze the time complexity of the given solution, we need to break it down into its components. First, consider the outer loop, which iterates over all even numbers from 2 up to number underscore people. Since the step size is 2, the loop performs number underscore people / 2 iterations, contributing a time complexity of O number underscore people. Next, the inner loop comes into play for each value of n. It iterates over even values of I from 0 to n2, performing approximately n/2 iterations for each n. Within the inner loop, the constant time operation dp n plus equals dp I asterisk dp n I2 is performed. This multiplication and addition take O1 time per iteration. Therefore, we can see that the time complexity depends on the combined work done by these loops, which we'll analyze further shortly. Now, let's calculate the total work done by the inner loop across all values of n. For a specific n, the inner loop performs n/2 iterations. If we sum this over all even values of n from 2 to number underscore people, we get the series 1 plus 2 plus 3 plus up to number underscore people slash 2. Using the formula for the sum of the first k natural numbers, this evaluates to number underscore people slash 2 asterisk number underscore people slash 2 plus 1 slash 2. When simplified, this results in a total time complexity of approximately O number underscore people slash 2 caret 2, which is equivalent to O number underscore people caret 2. For space complexity, the main contributor is the DP array, which has a size of number underscore people plus 1, requiring O number underscore people space. The rest of the variables like mod, n, and I only use constant space, so the overall space complexity remains O number underscore people. Comparing this dynamic programming approach to a naive solution highlights its efficiency. A brute force method would involve recursively generating all possible handshake pairings and checking for crossing handshakes. For number underscore people, this corresponds to calculating the nth Catalan number, which grows exponentially. Consequently, the time complexity for such an approach would be O 2 caret number underscore people. In contrast, the dynamic programming solution leverages previously computed results to significantly reduce the complexity to O number underscore people caret 2. This optimization is achieved by breaking the problem into smaller subproblems and avoiding redundant calculations, making the DP approach far more practical for larger inputs. Let's summarize the best, average, and worst-case scenarios for this algorithm. The best case occurs when number underscore people is 0. In this situation, the function immediately returns 1, which is a constant time operation with a complexity of O 1. In both the average and worst cases, when number underscore people is large, the algorithm performs all iterations of the nested loops. This results in a time complexity of O number underscore people caret 2. To understand why the time complexity is quadratic, consider that the outer loop runs number underscore people slash 2 times, and the inner loop for each n runs up to n slash 2 times. Summing over all these iterations mathematically confirms the O number underscore people caret 2 complexity. For space, the DP array remains the dominant factor, contributing to an overall space complexity of O number underscore people. In conclusion, this dynamic programming solution effectively balances time and space, providing an efficient and scalable approach compared to brute force methods. When solving this problem, there are a few common mistakes that can trip you up. First is forgetting to account for edge cases. For instance, what happens if there's an empty input, or if there's only one person, meaning no handshakes are possible? These situations can lead to runtime errors or incorrect answers if not handled properly. The solution is to always test your implementation with both minimal and maximal inputs to ensure robustness. Another frequent error arises from incorrect intersection logic. When checking if two handshakes intersect, the geometric conditions need to be applied precisely. Overlooking details, like how endpoints are compared, can result in false positives or negatives. To avoid this, use a clear mathematical approach for intersection checks. Lastly, relying on an inefficient brute force solution can be problematic, especially for larger inputs. A naive O n squared approach might work for small cases, but it will likely time out for larger ones. Instead, look for ways to optimize, such as using sorting, divide and conquer, or dynamic programming methods to improve performance. Another issue that often arises is misinterpreting the problem statement. Some candidates confuse the objective, whether it's to count crossings, avoid them, or determine all valid configurations without crossings. Misunderstanding the requirements can lead to entirely incorrect solutions. To avoid this, take the time to carefully read the prompt, jot down notes, and confirm your understanding before diving into the implementation. Additionally, overlooking symmetry can complicate the problem unnecessarily. For example, pairing person A with person B is the same as pairing person B with person A. Ignoring this can double the work or create redundant calculations. Recognizing symmetry allows you to simplify the problem, reduce computational overhead, and streamline your solution. In interviews, there are a few key strategies that can help you stand out when tackling this type of problem. First, always pay attention to the constraints given in the question. For smaller constraints, like n less than or equal to 1000, a brute force or slightly optimized solution might be acceptable. However, for larger constraints, such as n up to 1 million, you'll need a more efficient approach, like divide and conquer or segment trees. Visual aids are another powerful tool. Problems involving intersections or pairings are much easier to understand when represented with diagrams or graphs. Interviewers appreciate candidates who can effectively communicate their thought process with visual explanations. It's also a good idea to start with a brute force solution and clearly explain it before moving to optimizations. This demonstrates that you understand the problem thoroughly and approach it methodically. Don't forget to address edge cases explicitly during your explanation, as this shows critical thinking. Finally, be prepared to discuss trade-offs between time and space complexity. For instance, a dynamic programming solution might use more memory than a recursive approach with memoization, but it can be significantly faster. Showing you're aware of these trade-offs demonstrates maturity in problem solving. This problem shares similarities with several other challenges on LeetCode. For example, problems like meeting scheduler, merge intervals, non-overlapping intervals, and interval list intersections all involve reasoning about intervals or avoiding overlaps. Studying these problems can give you valuable insights and techniques that apply here as well. Now, let's talk about alternative approaches and their trade-offs. Divide and conquer is one such approach. By splitting the problem into smaller subproblems, such as dividing people into two groups and solving for each group separately, you can achieve a time complexity of n log n. However, merging the results can be tricky and may require careful handling. While this approach is well suited for larger inputs, it can be harder to implement compared to more straightforward methods. Dynamic programming is another powerful approach to consider. By defining states based on the number of people or pairs, you can systematically count valid configurations or minimize crossings. Depending on how you define your states, the complexity can range from n squared to even better. The trade-off, though, is that dynamic programming often requires more memory than other methods. On the other hand, a greedy algorithm might be simpler to implement. For instance, you could sort by start or end points and make locally optimal choices to pair people. This approach typically runs in n log n due to the sorting step, but it may fail for certain edge cases, so be cautious. Finally, a geometric line sweep algorithm is another highly efficient option. By sweeping through the handshakes and detecting intersections, you can achieve a time complexity of n log n. However, the implementation is more complex, making it less approachable for beginners. Each of these approaches has its own strengths and weaknesses, so choose based on the specific requirements and constraints of the problem. Great work! To wrap up, we've learned how dynamic programming and combinatorics come together to solve the handshakes that don't cross problem efficiently. Remember the role of Catalan numbers here, they're key to cracking similar problems. Thanks for watching, and we'll see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!